Yeah, good afternoon. Thank you very much, Eugene, and thanks so much, Matt, for the references to Tokamak Energy and emphasizing some of our innovations that we will get into now. So my name is Michael Ginsberg. I'm president of Tokamak Energy Inc., which is our American subsidiary. I'll get into the meat of our talk in a moment. Just to say, Tokamak Energy is a spinoff of the UK Atomic Energy Authority in 2009. So it's been around for about 15 years. I want to call out that we're joined here by a number of great people from Tokamak Energy. So we've got David Kingham, who is one of our founders. Thanks, David. And we've also got Greg Brittles, who is our principal magnet engineer. So he knows far more than all of us from TE at this point on this call. So you've got a great resource here. We've also got a couple of other members from our U.S. team. That's Andrew Schoen, our fusion development lead, and Aaron Washington, our technical program manager. So before I go, thanks guys. Before I go into the details of our innovations, I also want to mention, Tokamak Energy has been, working in the fusion space for quite some time. In the U.S., we are a member, awardee rather, of the Fusion Pilot Plant Program, milestone-based program that is part of the U.S. Department of Energy's Bold Decadal Vision for Fusion. As a part of the program, or I should say, as one of the reasons why we have developed magnet technology is largely around the rigorous demands of the fusion energy and the need to contain the plasma ions. So want to say that we've developed quite a bit at this point, and we are expanding rapidly in the U.S. We are also expanding rapidly into other sectors, and we're very interested in working with government and defense entities in the U.S. in particular, as well as with universities and labs to partner with on things like SBIR. So I want to put that right up front. I know the ask is at the end, but I just want to make that clear up front. And I'm going to go ahead and share my slides, and I'll lean on Greg a little bit on some of the very technical subjects. Just making sure you can all see.
Yep, looks good.
Great. So just briefly on myself, I know Matt did that in his introduction. Michael Ginsberg, again, I come from a background of developing kind of wide background, developing solar photovoltaic plants for about 15 years. Then I transitioned over to electrolysis plants or green hydrogen. Did a PhD in the technoeconomics of electrolysis and really about bridging the gap for a new technology. So that's really what has excited me about Tokamak Energy and the great history and credibility that this company brings to fusion and to HTS magnets, and very humbly, I should say as well. We have very recently announced a new business unit within our company that you can see here with our branding. It is called Tokamak Energy, or TE Magnetics. So we're very excited about that. That is a unit we have stood up within the company to essentially expand our magnet technology out, from both within fusion and out to other sectors like defense. So as Matt mentioned, there's this new or increasing focus on high temperature superconducting technology. Question is why? Why now? Well, within the fusion space, it's an absolute necessity. We need to get to these extremely high fields in order to contain that plasma energy for magnetically confined fusion devices. But outside of fusion, we see the potential for HTS to disrupt existing markets and generate new opportunities. So if you look at the sort of envelope in the top right, you can see the baseline low temperature superconductor for all three relevant parameters having certain limitations when it comes to the amount of current density, temperature at which it operates, and magnetic field. So HTS really expands that envelope and can be a major game changer when it comes to what it can do for certain applications. Broadly speaking, there are four major categories here of interest. You get higher energy density or higher fields and more compact magnets than other technologies. This means that you can be a lot more modular, which I know is of extreme importance to missions and operationally. Higher fields, we'll talk about some of the numbers, but Tokamak Energy has achieved really the highest field in any magnet worldwide, and we'll talk about what we did to do that. Higher temperature operation. It's always a bit confusing, but at least it was to me when I first started to get familiar with it. But high temperature is compared to the existing low temperature superconductors. So instead of cooling down to 4 Kelvin, which is LTS, we cool down to 20 Kelvin. Well, that is actually a 5 times cooling efficiency, so huge thermal gain for that. And it does mean that we don't need to use liquid cryogens. So we have gaseous cryogens, which really reduces the balance of plant cost and makes it a lot easier to use for many different applications. We also use a lot less rare earth metals as compared to permanent magnets, such as those in wind turbines with permanent magnet generators. Feel free to, of course, interrupt me at any point.
This is Eugene. I'm going to interrupt you really quick. So,
Sure.
So that change from liquid to gas, does that affect volume size at all?
Yeah, and Greg, feel free to chime in. Essentially, we're looking quite a bit at the way that we cool this, and in terms of the absolute volume that you need. With a liquid cryogen, you're gonna need to have a separate tank, etc. We've actually designed our cooling to be much more embedded.
The way that the helium is used in the system is very much like the way that the gases are used in your refrigerator at home. They're basically a working fluid that moves around in a closed circuit, and there's almost none of it. You need a tiny amount of helium gas to just move the heat from one place to the other, and it just gets pumped around and recirculated. You don't lose any. So it completely eliminates this issue of needing a rare commodity that's actually in very short supply in the world.
Excuse me.
I think that the volume question, I know you're coming from, Eugene. I think that the way we've designed it does limit that sort of extra space that you're thinking about there.
Correct. Okay, thank you.
Yeah. So really, why now? I sort of mentioned this quite a bit, but we see HTS technology as one of the key enablers for the realization of commercial fusion. In other words, getting to net energy gain. That's why David and team over the last 15 years have developed HTS technology. It is extremely important, especially for spherical tokamaks, low aspect ratio. You've got rigorous demands on your device. So we need to contain that energy to be very efficient, get a high bootstrap. Or self-sustaining, energy. With HTS, why is this relevant now outside of fusion? Well, this is a prime example of a subsystem technology that has such a major potential impact outside of fusion, right? So, within fusion, it is the main enabler for why we are able to get to in the near term, in our view, net energy gain in a magnetically confined device. In terms of the cost, the tape that we use, which is essentially the building block for our complete magnet system, that demand is increasing, largely, hopefully, in part because of the demand we're putting onto the market and the supply chain. We work closely with a number of U.S. manufacturers, some of them who might be on the line, like Medox. We're talking to. We work closely with Furukawa, which has a subsidiary in the U.S. in New York called Superpower. But essentially, the tape is critical, and the cost of the tape coming down is another main reason why we think this will revolutionize a lot of sectors. And really high performance and robust. So largely, I know a lot of the feedback and criticism, I should say, about HTS that I've heard recently from those who've looked at it before, especially in defense, is that it quenches, it essentially loses its superconductivity, it fails in mission. And that's something we have effectively, and Greg, feel free to correct me, but we effectively overcome both through our great design and our ability to model and predict where quench can happen, and we're able to deal with a lot of different tapes of different qualities and different manufacturers.
So what is the benefit of a tape over a circular conductor?
I'm gonna let Greg talk about this slide a little bit, and then he'll answer that question in this slide actually.
Oh, okay, sorry about that.
Yeah.
I would say the answer to your question is we don't actually get the choice with this material. It is a tape, and that's the end of it.
I just came up here to get on this call.
Oh, sorry. I think someone may need to mute, unless you know something about tapes versus wires. Yeah. So the way that the tape is grown is by a film growth technique that requires a sort of single crystalline texture. So the suppliers, many of whom are on the call today, have figured out ways of depositing this crystal onto a thin tape. No one yet knows how to make it into a wire with the same properties, and many would like to. But the bottom line is it's a tape and it's no problem. We can use it.
Yeah, thanks, Greg. And I think you can see here essentially, a cutaway of the tape. You can see that the REBCO stands for rare earth barium copper oxide. That's essentially this 1 to 3 micrometer thick layer. That is the superconductive layer, but you can also see a number of different layers in here as well that comprise the tape. But this is how we receive it. Feel free to talk about the slide, Greg. But essentially, what we're seeing here is that if you look at ITER, right, in France, we're essentially looking at a regime here where you need the liquid helium, where we talked about liquid cryogens being more challenging and energy intensive, and much lower when it comes to magnetic field limit. But if you look at the blue line with the REBCO HTS, you can dramatically improve your magnetic field in evident on these tapes.
Perfect. Nothing more to
Thanks,
add.
Greg.
It expands expands the window of operation hugely, and we
Exactly.
are capitalizing on that. Yep.
Kind of why REBCO? Yeah. Oh, go ahead.
So sorry. Renaissance Fusion is saying that they're trying to build wider tapes, wider than 12 millimeters. Can anyone comment, maybe in the supplier base or Greg, or on the feasibility of that? Because I'm curious.
I would definitely invite some of the tape suppliers who are online to comment. But it's very challenging. So the growth process is a very tight processing window that's difficult to maintain over a 12 millimeter width, which is the current standard. And of course, many suppliers want to go to the wider widths so that you can get more material through the deposition machines faster and basically reduce the tape costs by that mechanism. But it is just very challenging to maintain the quality of the wire or the crystal across the full width. Any tape suppliers on the line want to make any comment? No, you're stuck with me. It's very difficult, but absolutely possible.
So,
Right. Thank you.
Greg, this is Eugene. If you wouldn't mind sending me some information about that, and I'll pass that around and see if I can't get some solutions even from an IC manufacturing standpoint.
Yeah, sure. I'll send something around. David?
Yeah, I might comment at this point. These tapes carry huge currents, thousands of amps in a single tape. So often in magnet applications, people are cutting them down to 4 millimeters or less, so that the current is a manageable current. So for some applications, very wide tapes might be great. But for a huge number of magnet applications, 12 millimeter tape is ideal, and sometimes it'll be cut down further.
Okay.
Yeah, absolutely right. Yeah, in fact, the tremendous current carrying ability of the tapes makes it very difficult to actually measure how much current they can fundamentally carry, which is a nice problem to have.
So David said that the tapes get cut down further. So then is it still cost effective if I could make a 36 millimeter tape Is it still cost effective to do that and cut it into 3 12-inch or 12 millimeter strips?
Yes.
Okay.
So there are techniques now that basically allow you to slit the tape down either by laser or mechanical means with very little damage to the edges. There are groups of Florida State University and the Highfield Lab have done a lot of research into this kind of slitting and best methods and what cracks you get at the edges and what the ramifications are in magnets. But fundamentally, if you can make the tape very wide and then slit it down with minimal damage to a narrow width, that's the most economically viable route forward.
All right, thank you.
And I would just add, we work closely with suppliers on acceptance testing, essentially to qualify and what are the different ways we can characterize and test these tapes that we receive. It is a maturing market and industry, so we're hoping to advance it.
So now, what about Oak Ridge and Kansas City, the DOE labs? Do you work with them at all? Because they have some phenomenal facilities there at those two.
Yeah, so we do work closely with Oak Ridge National Lab. And feel free to chime in, Greg.
Yeah, I know that Oak Ridge do a lot of work on irradiation studies of superconductors, which is a very important topic for fusion because the magnets have to stand up to the radiation that the plasma emits when it fuses. So it's a big field, and they're doing a lot of research in that.
I would just add, we did a study with Sandia National Lab a couple of years ago now, testing a gamma irradiation test of the magnets. And that was successful. So again, I probably will defer to Greg a little bit because he was a big part of this. But what I will say is that our timeline essentially has grown from looking at LTS, low temperature superconducting technology, and not just trying to adapt that to the needs of that we face today with magnetic confined fusion, but we're sort of going back to first principles and reinventing the way that we wind the tapes to create a magnet system. So you'll see across this, over time, we have gradually grown from offering non-insulated tapes to partially and fully insulated, and essentially that is a way in which we can tune the tapes to ramp at different speeds or rates. This evolution as a company, I would say, has manifested in what you can see on the screen, which is going from developing the IP around coils to building full magnet systems, which you can see with Demo 2, which was partial insulation test to test our quench resistance through this partial insulation system. Demo 3, non-insulated. And right now we are in final stages of Demo 4, which is very exciting. That is a full set of TF and PF field coils that we can test essentially to essentially de-risk our magnet system for future fusion device and prove out our quench protection. We are working also on an ultra high field demonstrator, and so I think it's quite impressive to see what we've been able to do. Both with specific individual magnets as well as full magnet systems. And I'll speak on the next slide about some of the world records we've achieved. Anything else you want to add to this one, Greg?
Thanks, Michael. No, I think that covered it very well. I would just say we've just speaking to some of the comments earlier about the way in which we've done technology development. It marries up with what's been said. We move fast. We build things. We test them. We develop software. So we have some of the best software in the world for modeling the hardest effects to simulate in HTS magnets. These are things like quench. So what happens when a magnet suddenly loses superconductivity, which, as it happens, is actually very difficult to do in an HTS magnet because they're hyper stable. They don't quench by themselves. And yeah, so we've been walking through the manufacturing process, the quench protection story. We've been developing jointing technology, current sharing within cables, and as Michael said, we're now tackling some of the bigger integration challenges in building a full Tokamak configuration magnet. So yeah, so we're walking boldly through and building things, testing them, and simulating them to take us on our path.
Thanks, Greg. I'd also add, it's exciting to me, especially that we are really moving forward in large-scale manufacturing. So process and tooling, as you can see. So we are absolutely focused on getting this out there into relevant industries and working to make these, essentially as off the shelf as possible when it comes to design. I mean, the earlier comment around we don't want to get caught in forever modeling exercises. So we're really keen to get that to get our manufacturing upscaled, and we are working on that, especially with U.S. partners. So I'll speak to this, and this is sort of the greatest hits that are really great to touch on. So we were formed in 2009. In 2015, we built our first Tokamak. It was an HTS Tokamak. It sustained a pulse for over 24 hours in terms of plasma ion pulse. So that that was a great achievement. And in 2017, we built our next device, which is our current one, Spherical Tokamak 40 or ST40. In 2019, we achieved a world record 24 Tesla with this HTS technology, and we've actually pushed it even greater than that. So actually, we validated a 26.2 Tesla test at CERN. So increasing field strengths even today. We are really world leading in terms of our magnet quench protection, which is probably the most important thing. If you're driving a car, you want to make sure it works while you're driving it. You can't accept quench at any point for an operational device of any kind. And we built the world's first set of advanced HTS coils in a Tokamak configuration, as you saw in the previous slide. And we are working on an ultra high field magnet at the moment. Within our magnet solutions, we have a number of different patent areas. Over $50 million in terms of R&D has been spent to date. Just 10 million in just the last year. We are increasingly focused on commercializing our HTS technology, as I've mentioned, with over 200 patents granted. You can see about 20 in magnet structure and manufacture. As Greg mentioned, a lot of our value is in the partial insulation and current sharing schemes that are in large part why we are able to prevent quench, essentially largely around allowing the potential overheating of a specific area of our magnet system from losing superconductivity and allowing that current to be shared across the coil. Quench detection and management as well. So we do work with a large number of other companies to help them to model out and build their systems. So we're in early stages of doing that with other fusion companies as well. So owing to a large history and amount of investment into this, and we believe that with fusion, it's such a challenging thing to achieve. We should all benefit from the expertise we've developed in our areas, and likewise, we always look to partner with others outside of our specific area of expertise. So I think it's good for that slide. So I will let Greg talk about the details around some of our different types of magnets. This is largely specifically around the ramp rates and the amount of insulation that we put in. We've developed a specific way of ramping the magnets, and so we are now offering, in addition to modeling and analysis, system design. We're offering prototype development and very shortly manufacture and supply. So we want to be able to, come to a customer and say, you need this kind of magnet or magnet system. We can provide that for you, recognizing as well that there is still a good deal of, application engineering that goes into this, but this gives you a good overview of the different types of services that we provide as a company, from modeling, asymmetric modeling, to 3D quench simulation models. I know Greg does quite a bit of that. Coupled electromagnet and thermal network solvers, and bespoke coil optimization tools. So you're going to need certain size coils based on your application. For the large tokamaks in the future, you're going to need very, very large coils. And so I think we've essentially distilled our technology into 8 different pillars we talked about, but I want to touch on these and their applications to defense. So modular, we can design these to be incredibly modular and energy efficient, and customized so that they are mission relevant, robust, right? So these are solder consolidated monolithic pancakes that you can see on the right here, high thermal conductivity. Scalable, so we can scale these, these slices essentially, add more pancakes, also change the sizes and shapes. So working with other types of fusion designs, whether that be stellarators, or other types of fusion architectures, but also for defense applications, whether that be motors or rail guns, etc. Configurable. Defect tolerance. So as I mentioned earlier, we can take different tapes, right, from different manufacturers, and these tapes are, the magnet systems we design are incredibly robust and resistant to defects within the tapes. Although we work closely with the manufacturers to improve their characterization and quality control. But we do pride ourselves on being able to work across manufacturers, and that also reduces costs down the road when you can source from different manufacturers. Fault tolerant. So I sort of briefly touched on this, but we can handle de-energization. So when you've got an interruption in current. As well as tunable. And I think tunable is the next few slides where we really talk about the way that we insulate, between the turns of the tape, and being able to ramp quickly or slowly based on need. And then finally, no liquid cryogen. So using gaseous cryogen, and it makes for a lower cost system overall. So we've got 3 product categories. The first is fixed field, second sweeping field, and the third is fast ramping. Greg, if you can go ahead and kind of talk through these differences, that'd be great.
Yep, no problem. So
right, I'm gonna stop you here for just a second.
Yep.
Yeah.
So 2 slides back, Michael, you had talked about that you could go into a customer's facility and talk to them about what their needs were, design them, build it, and implement it. What is that? What is the time frame for that? Are you looking at 6 months, 12 months, 18 months from design to installation? Just to get an idea.
So it's hard. So I know you want a firm answer here, but what really depends on which customer, of course, whether the application has been built out. We've got a good deal of modeling already in place for certain applications, but we want to work with users, right? So like, if that's NAVFAC or if that's ONR or another agency, if they come to us with a specific need, they say, hey, we need it to do this. Tell us what those needs are. We can throw a good amount of resource at that. If we see there's real resource behind it, frankly. So the speed at which we can do this is largely based on the appetite of the customer. I would say. Now we've got a limited amount of people. So as a company, we've got 300 people. I would venture to say we've got about 70 of those who are working within that Magnets business unit. But again, we are looking to grow this business within the defense space in the U.S. I was going to mention it later, but we are currently about to begin a DARPA project. So that's kind of our entree into working in the U.S. defense space. but if there is a customer that comes to us, we can go fast if we want to. And Greg, feel free to add to our process at the moment.
Yeah, so I think one of the biggest thing that customers are looking for us to do in the first instance is either prototyping. So this might be development of cables for magnetic confinement fusion devices, for example, or it might be doing the hardest simulations that require the most advanced software. And these studies typically can be completed within a couple of months, working closely with the customer to understand their specific needs, understand what they actually want out of the magnets, rather than to just we don't like to just give the customer the solution they've initially asked for. We will always have discussions with the customer on what they actually want the magnets to do, and even help them to develop the magnet solution that's going to deliver the best value. So typically that's a kind of few months process. And to give one example, actually, we actually worked with the Paul Scherrer Institute in Switzerland, which is an accelerator development facility, particle accelerator development facility. They were looking to integrate HTS magnets into future accelerators, and we actually licensed our technology to them. In fact, the technology that you see on the screen here is basically what we licensed to them. And over the course of a year, we, during COVID, I will say actually, so fully remotely, we actually licensed our technology. We told them how they could go about building a coil like this for themselves. And a year later, they had an 18 Tesla no insulation magnet working at their facility in Switzerland. So just an example of the kind of things that we're doing.
Okay, so then just to take it one step further, so I understand the variability depending on the size and the requirements. At the end of this design stage that you just finished, where you've come up and you've agreed to a system, can you give them a time frame at which you'll be able to implement it? So that's you know.
Yeah, absolutely. I think we couldn't say on this call, the time frame will be X, because it completely depends on the complexity of the system. It might be kind of 1 year or something of that order to do something that's on the screen, or it might be several years if it's a very, very complex.
And I fully understand.
Yeah.
Because I've been in those meetings where, people have looked at me and said, well, you do this for a living. You should be able to tell me how much it's going to cost me. And, and I always want to turn and look at them and say, yeah, it's going to be $10 million. But if you give me 48 hours, I could probably get that price down.
Yeah. I mean, it's also reasonable to say that we're just launching this business unit. Our primary mission was development of fusion magnets for ourselves, and we've spun out this business unit, and it's going well so far. But we don't have a huge track record of delivering commercial magnets to customers, because this is the start of our journey. So ask us again in a few years when we've delivered a large number of successful projects.
We'll do that. All right, go ahead.
Right. Okay, so we have our three different categories of types of magnet, and they all have their strengths. So fixed field magnets are all based on the no insulation technology. So these are, if you want a magnet that's going to generate the absolute maximum magnetic field for the least amount of HTS tape, it has the least probability of ever encountering a quench. For example, it can survive a power cut for some period of time, and it will continue to remain at field. Then this is basically the technology that's needed. So we produced in 2019 a 24 Tesla HTS coil operating at 20 Kelvin. That was the first time anyone had ever exceeded 20 Kelvin at 20 Tesla at 20 Kelvin, which is fusion field. So we produced this coil. We ramped it several times. There was no degradation. And basically, if you want a strong magnetic field that's just going to be stable, then this is the one. Michael, did you want to talk about applications for these sort of magnets?
Yeah, I'll touch on that a little bit later, but you can see that where, as I mentioned earlier, the technology has the ability to transform a market. So in this one, sort of starting from the defense side, magnetohydrodynamic drive. I'll talk about that later on in the context of our DARPA project, but also MHD for satellite thruster propulsion. You can see we're, in conversations in two other sectors here where, a fixed field magnet is relevant. That's ultra high field NMR. Really can be very powerful for imaging and manufacturing as well. For instance, for magnetic separation of important minerals, as well as industrial processing.
Yeah. One last comment, I guess, actually on that slide, Michael, if you wouldn't mind. The image in the top right there is actually a coil module that we sliced away a quarter of the coil, actually just to inspect the surface of the windings. But we decided we would do a wild test and actually see if it still superconducts and still performs. And to our shock, it did. It remains a functional magnet that goes to half the field that it went to before. So and we did a similar kind of test where we actually drilled holes through the coils and then tested the coils afterwards and proved that the coils remains functional. It just loses a few turns of effective current capacity. So this is the crazy territory of forget what you thought you knew about superconducting magnets, forget that they're sensitive, delicate instruments that can be destabilized by a pin drop from a few centimeters, which is the old adage. This is not the case anymore. You could drop a bowling ball from a meter and these would not quench. Okay, that's it.
Yeah, thanks.
Okay, so there are many applications where it's desirable to be able to change the magnetic field quickly. And in the previous class of magnets, they were all based on the no insulation technology. So this is where we join together the turns with a very low resistance connection that allows the current to share around the turns to go around things like these gross defects that you've intentionally introduced in wild tests. So there are applications where you want to make larger magnets that ramp much more quickly, and we can't employ that technology in those magnets because it would take too long to ramp. So what we developed is a method of actually increasing the turn-to-turn resistance by just enough that you maintain many of those stability benefits, so the coils remain extremely stable, but whilst also allowing you to ramp the coils more quickly. So the first time we actually deployed this technology, and this forms part of our patent portfolio, it was in the Demo 2 magnet project. So this was a coil that had a 180 millimeter inner diameter, 300 millimeter outer diameter. It was a six pancake stack, and we were able to ramp this in a few minutes up to 10 Tesla, compared to a few hours for the no insulation coils. The other thing that we did was we did some quench testing on this coil, because the partial insulation not only acts as our means of ramping the coils up quicker, but it also acts as our kind of pressure relief valve within the coil that allows current to flow radially from turn to turn in the event of a quench to actually distribute the energy nice and uniformly so that the coil isn't damaged if you have to rapidly de-energize it. So one of the things that we did was we actually embedded a heater within the pancakes that were most challenged. We ramped the coil up to the point where it was reaching the critical current, so the limit of those turns, and we could see the voltage taps on our sensors rising, so we knew we were at the point where the superconductor was at its limit, and we started to fire heater pulses into those turns. And to our amazement, we started off at 1 joule, 10 joules, we cranked it up to 100 joules, and the heater burned out before anything substantial happened to the coil. We were not able to quench the coil by this method. And this is remarkable. Typically, if this was a low temperature superconducting magnet, you'd be talking about tens of microjoules that is required to destabilize the magnet. So talking about tens and hundreds of joules is a completely different paradigm for magnets. So they're extremely stable. So we've now deployed this in our Demo 4 TF coils, So this is an example of a coil that has to be ramped up from 0 to peak field in basically a day, and then it just has to stay on for a long period of time. So that's perfect for this application where we want a nice steady field. It doesn't have to change very quickly, and we want to be able to quench protect the magnets. So that's that application.
Yeah, and just adding to that, you can see in the target applications, now we're getting into applications that, for instance, with fusion, where you need to modify your fields based on changing parameters and conditions with that plasma energy. That's obviously really important. And also with transportation, in particular maglev, opens up new opportunities for high speed train transportation.
Yeah,
yeah.
I'll make you go back one more time. I always remember
no,
more useful things to say as soon as you've moved on. So the other key advantage of the partial insulation approach is that it limits voltages to extremely low values. So typically with conventional superconducting systems, in order to extract the energy quickly from a high energy magnet, you have to apply a very high voltage in order to suck the energy out, or if left unattended, the magnet will do that for you, make a very high voltage, and this can create breakdown scenarios, arcing, and it's quite hard to manage. So this has really plagued for example, the JT60 project in Japan. It's been one of the key challenges of the ITER Tokamak is managing very high voltages. So we've learned from the steps that those important projects have made, and we're now benefiting from this in making coils that can be protected and de-energized with voltages that are very low. In this case, Demo 2 experienced less than 10 volts, whilst the energy was dumped in a few hundred milliseconds. So yeah, quite remarkable. You can really change the slide now. I promise.
Thanks,
I'm finished.
No, it's fantastic.
Thank you. Okay, so the last item on the menu is the fast ramping magnet. So there are lots of applications for coils that require you to change the field a good degree more quickly. So in fusion devices, for example, the poloidal field coils have to be ramped up in sync with the plasma current. And that means that they have to change fairly quickly. Similarly, the central solenoid of a tokamak has to be ramped quickly in order to induce current flow in the plasma. So in these scenarios, we can't make use of no insulation and partial insulation. We have to demand that the current goes round the circuit straight away. And here we have full insulation technology. So we've solved some of the the key challenges of full insulation coils, which is making sure that you can still quench protect the coils even when you don't have partial insulation to lean on. So we've now deployed this in our Demo 4 poloidal field coils, which are liquid nitrogen tested and currently being installed on the system.
Perfect. Thanks. Yeah, and you can also start to see in looking at motors and generators as needing this kind of fast ramp as well. Perfect. Yeah, so thank you again, Greg. I think we have, as I mentioned earlier, been really looking to work increasingly with the U.S. defense sector. As you can see, Tokamak Energy, I think, brings a materially better HTS to the table here when it comes to looking at all these applications, and we've just started having conversations with different defense equities. As I mentioned earlier, we have a DARPA project that's just started that is for magnetohydrodynamic drive. It's something that the military has looked at before using LTS. Essentially using electrodes and a charge underwater with a submarine, and with Lorentz force, a magnetic field acting against that charge for magnetically propelled silent propulsion in a submarine. The big difference between LTS and HTS is essentially it goes from something like 5 to 10% efficient to 80+% efficient for that process. We think it's really, really game changing. We also are talking to different equities around other applications of interest, things like launchers, shaped charges, potentially quench guns or rail guns, you know, you name it. Also electric motor technology, when you know, for aircraft carriers, electromagnetic aircraft launch systems, to make these systems a lot more efficient. And we also feel there's a lot of great applications in space, whether that be magnetotorquer, essentially using magnetic dipole, interfacing with the sort of ambient magnetic field of the Earth to generate torque, electromagnetic tethers as well, so you can accelerate or decelerate, or you know, provide electrical energy, and plasma thrusters, which is essentially using those Lorentz forces against an ionized gas material in space. So there's a plethora of applications. I will be very direct. We are, you know, relatively new in our outreach to defense. We do not know what we don't know. So we've been talking to a lot of defense folks in the U.S., but we don't know what missions are needing today. So we need you to, you know, to kind of reach out to us, let us know, and then, you know, we can have Greg and others in our team figure out what makes the most sense. So when it comes to, you know, all these applications, we want to help, and we're very, very excited about bringing this HTS technology to the market. And so I think that's the end of the presentation. I've left all of our contact information up, but would love to use the remaining time to talk through any questions that folks on the call may have.
All right, thank you, Michael, Greg, that was great. So does anybody have any questions? Please unmute, ask your questions. All right, so I want to bring in, while we're waiting, let's see, Adrian Timms.
Times, what's up?
You're my space expert, so talk to me.
What about I'm high temperature superconducting tape can be used for energy storage, but I'm more focused on the launcher side than on the satellites side.
Right, but now some of the applications dealt with propulsion, so that was my question.
Yes, I think so. So in principle, the application there would be utilizing something like quench in order to inject a huge amount of force into a projectile and allow it to be launched. So one of the interesting things that we found when we were first testing our no insulation coil technology is the way that quench actually propagated from coil to coil in a stack. So you could dump the energy in the coils within about 100 milliseconds in a very sequential manner, which is basically exactly what you need in order to actually launch a device. So it's not something that I've looked into in huge detail, the sort of the dynamics of, but the principle is quite clear there.
Right. Well, what about going the other way? Rather than dumping a high amount of energy in a short time, what's the longevity of the tapes? Could you say keep up a magnetic field for a year, solid?
Oh yeah, yeah. I mean, you mean just constantly at magnetic field?
Yeah, constantly
Yeah.
have magnetic or containment, say for an ion engine.
Yeah, absolutely. Yeah. So that's the whole advantage of HTS is it allows you to generate the strongest magnetic fields that you can keep on with very low power consumption all the time.
Well, not necessarily the strongest fields, although that might help.
Well,
But
yes,
more can you keep for a very, very, very lightweight compared to the alternatives? Have the magnetic field strength necessary to confine energized particles generated by some other means blowing through a chamber so that they come out as exhaust in a specific direction as opposed to blowing all over the place.
So like an ion thruster.
That is the
Yeah.
basics of an ion selector. Obviously, I'm skipping over a lot of details, but yeah, if you're looking for new applications, that would be one of them.
Yeah, absolutely. So we actually have worked with a company in Oxfordshire on this called Mag Drive Space. And so that they have a similar concept. They just want the strongest possible magnet with the lowest possible weight that they can send into space in order to thrust satellites around, so make small course adjustments. And one of the things that we were able to do with them is to validate that you can launch HTS coils into space and that they can survive the temperature transients and most importantly, the shaking. So the mechanical vibrations that happen when you launch a coil into space. I don't suppose you're, yeah. Oh yeah. So that's what you're looking at, right? For space.
Basically, yeah.
Yeah.
So how are you on not just generating the magnetic field, but potentially using this to ionize some of the particles? If you got anything on that, contact me offline. I'll drop my email into the chat right here, because we do have a potential application that may be enabled by your coils.
Yeah. Okay. I absolutely can do that. We will reach out to you. Thank you.
Okay. Yeah, I'll put you guys together.
That's great. Thank you.
So Jeremy Tootin, I see you're unmuted. Before I ask my next question, does anybody else have a question? Go ahead, Jeremy.
Eugene. Okay, so I'm curious about radiation resistance. I know that if you're containing fusion or something else, great, you should keep all the radiation from harming your coil. But in space, there's a lot of incident radiation from other sources that aren't going to be inside, aren't going to be where your magnetic field is ideally protected. Do these materials have crystalline structure changes induced by gamma or neutron radiation or anything else?
Okay, so good question. So what we know is that neutrons will degrade HTS, and there's been a lot of work on this coming at it from a lot of different angles. It's basically until this year stroke next year, it's basically been impossible to actually do the killer experiment, which is to have a cryogenically cooled HTS coil carrying current at field being irradiated with a fusion spectrum of neutrons. But so what people have done is they've taken tapes and they've put them in fission reactors at about 60 degrees Celsius, so warm, and they've then tested them offline after they've kind of cooled down enough that you can put them in the test rig. And the best data that we have on the degradation rate is based on those tests. The other thing that people have done, including at MIT and at Oxford University, is to use ions as a proxy for neutrons. So there you can put tapes cold and energized and expose them to energetic ions that are a decent proxy for what happens when neutrons hit a tape. And those have broadly supported the data that's come out of the fission experiments. And then the last thing is to do simulations. So simulations of how particles collide with the crystal, where the atoms end up going. And of course, the superconductor is very sensitive to exactly where all of the atoms are in the crystal. And so you can't mechanistically say, okay, now it doesn't superconduct and now it does based on where the atoms are. But we have a pretty good understanding of what the conditions are required for it to superconduct. So yeah, in a nutshell, there's a pretty good body of evidence for how long tapes will last as a function of neutron irradiation. As Michael said, gamma irradiation, we took a coil test assembly over to Sandia National Labs. We basically had coils there cold and energized and irradiated them for the full power lifetime of a fusion reactor. So we have that data. What we're saying is that the results are positive. We're not at a point where we can actually release the results of that data because we're analyzing it and we're considering what to do with that information. But it's safe to say that we haven't packed up and gone home. So the results were pretty good. So I hope that answers your question well enough on irradiation effects. Is there anything else I can say?
No, that's a great answer, and I'll bet what I'm going to follow up with is already covered by your. We can't say more at the moment, but I'm curious. Assuming there is a failure point, is it graceful? Is it a nice even degradation you can see, or is there a critical point where, at some point of radiation exposure, you fall off a cliff and the fail point is critical?
I think I can't say. I'm sorry, Jeremy. I would love to. As a scientist, I would love to dig into what's happening and have an open discussion, but I'm forbidden.
Fully understand. Thank you.
Thanks.
So that reminded me, there's another application you might look into: radiation shielding for manned space stations. Here, let me link to an article that's got 3 of the ones NASA's looking at. So you might want to contact the companies mentioned in this article, just to see, do they have radiation protection solutions? If not, or would they be willing to talk to you about having you be on? They're all hypothetical ones. I mean, Axiom's got some stuff on the ISS, but these are the intended replacements for ISS sometime down the road, not terribly mapped out, but they are funded efforts. So
that's great. Thank you very much. Yeah, we'll look into that. That's great. Yeah, again,
right.
it's power, weight,
Yeah.
efficiency. That's what counts. Yep.
Anyone else? Questions, comments, thoughts, concerns?
I thought that was great presentation, guys. That's what I thought.
I know we hadn't talked about SMES, and Jeremy and Ryan. I know you guys are DOE, but and Greg and Michael. So in a hydro plant, you pump water uphill for energy storage. In a thermal, you generate steam as energy storage. Could this replace or provide alternatives for energy storage at those facilities? And the other thing is wireless power transfer is becoming a reality. And if I'm correct, and I'm not a scientist, but I believe that pulsing large amounts of power is more efficient than providing a steady stream of power. Could you use these in wireless power transfer applications, energy storage, even not necessarily at the plant, but at a transfer station?
So I can't make any particular comments on the wireless transfer aspect, other than to say the challenge I would envisage there is that superconductors only superconduct in the pure sense when the current is DC. So when the current is changing, the material is experiencing heating effects.
Right, but it would be DC converted to microwave.
Okay. Yeah, completely out of my realm of expertise. I'm afraid. Sorry to give a disappointing answer.
That's okay. I can talk to the experts.
Yeah, thanks. On SMES, so a comment actually on there was a discussion earlier I might be able to lean into a little bit on the sort of the stray field that you get from a SMES-like device. So one of the common topologies for magnetic energy stories is the toroid. It's a toroidal-based magnet arrangement tends to be the one that produces the most stored energy per unit conductor, and actually it's the one that also limits the stray field the most. So to give you an impression, the demo for spherical Tokamak magnet set, Michael, I don't suppose you have the slides back to hand. You could if you could bring up the that it would help.
Let me see here.
So the demo 4 system is roughly a meter and a half across. Yeah, you'll see.
On you thinking?
Maybe slide 7 could be good. So you can see it in the top right image there. Oh, there
Sorry.
we
I lost it. One moment.
go.
There we go from
Yeah.
the current slide.
So the top right image there is the beginnings of the toroidal field magnet assembly process that's now actually quite mature. So there's 14 toroidal field limbs basically mounted on a spine like that, and the diameter of that is roughly a meter, something like that, a meter and a half. And roughly speaking, this might get to about 18 Tesla. We'll find out when we turn it on. It's a test bed. But the stray field from this, the 5 Gauss line, is not much further out than the actual system itself. So we have a 20 meter by 20 meter room that contains the 5 Gauss line, which is the completely safe to exist in as a human line. And that's dominated actually by the poloidal field coils that go around the outside of that system, so not the toroidal field coil itself. So what I'm trying to say is significantly less than a 10 meter by 10 meter room. Sorry, not 20 meter by 20 meter. Significantly less than a 10 meter by 10 meter room for the stray field containment. From a toroid such as this, which stores 16 megajoules of stored energy. So probably you're talking about a few meters by a few meters for the safe magnetic field radius. Yeah, and the thing the place that HTS SMES can possibly have a role in is in it's probably not in kind of mass energy storage, because the superconductor is expensive, and pumping water uphill is or compressed gas in a cavern is the mass large scale solution that we definitely can't compete with. But for high power, kind of very rapid injection of energy applications, that's where I think HTS SMES can possibly have a role.
Okay,
Yeah.
so that answers that question.
Yeah.
All right, anyone else?
So you're not comparing to gravitational storage, but what about, say, lithium-ion batteries? Roughly, for, say, storing power over a few hours, how does your system compare? Not in exact numbers, just way better, way worse, roughly the same, what?
I honestly don't know. I couldn't tell you. All I can say is that the system is 16 megajoules, and it's roughly a meter and a half in major dimension. I genuinely don't know what the energy density is of lithium ion and how it compares. We can do the sums though.
Yeah.
That's another thing that gets bandied about is, superconductors will allow much denser energy storage. If you can crack that, I'm not saying you can, just something to look at. If you can crack that, oh boy, are there applications there.
Yeah.
Yeah, Matt, you know something about that, right?
Yeah. I was just going to say that it was very hard to crack diesel. Diesel's very high energy density. 25 Tesla for 250 megajoules. I thought that was high, and then I looked at what diesel's density is, and it's really high. So yes, SMES has been done before. I mentioned the Japanese work and the Peter Cho work at the Navy in the 90s. And I know Livermore has some SMES research, so there's open papers on that. And I know there's a number of startups out there doing SMES that Tom Painter knows, and maybe he could mention them.
Okay, I'm gonna interrupt you here for just a second and put this to the diehards that are still here. So what do you think about if we continue this process? So now we've talked about HTS and we've talked about superconducting magnets. What if 2 weeks from now, 3 weeks from now, we do a SMES forum, and then 2-3 weeks after that, we wrap it up with a fusion forum, and just follow that. So going back to everybody that's on here now, if you wouldn't mind putting in the chat whether that would be of interest or not. Otherwise, I'll make the call that we'll go ahead and do it, as long as everybody's in agreement.
Sounds good to me.
Eugene, if you want to do a fusion one, I can do a fusion presentation.
Yeah, no, that's what I'm thinking.
Yeah.
That's what I'm thinking is if we just go through those stages, because that's what we did. We started with HTS and magnets, superconducting magnets, and now we take it to the next step, which is magnetic energy storage. And then the next stage after that is to discuss fusion.
Yeah. With SMES, there are better folks to talk than me.
Right. No, and Tom's on here, and I'm sure Tom.
Yes, SMES is not really my area, but I'd be happy to sit in on the magnet parts of it.
So now, would there be a conflict between Tokamak and Canyon?
In what respect? Sorry.
To have you both on a call?
Oh no, not at all. No.
Okay, I just want
We're
to.
No. We talk with these. Yeah.
Okay.
We're all friends. We know each other
Okay.
well.
No,
Yeah.
I just want to make sure. I just want to make sure that I don't
asking.
step on anyone's toes. So no. So that sounds good. I think that'd be a good way to go. Michael's back on. Do you agree, Michael?
So just caught the last bit of that, but happy to have introductions, of course. Sorry, we had a storm here. Yeah.
The idea is that in 2 or 3 weeks we do a SMES presentation where we focus on magnetic energy storage for them, and then 2 to 3 weeks after that we just do a fusion, and we take this all the way to the end.
Sure. Sounds great.
All right.
Awesome. Thank you for
Okay,
having us.
so 2 people commented and they both agreed. They both said good. So yeah, so I think that we'll go with that, and I'll work out the details. And that'll be it. So I do want to thank everybody for being here. I want to thank the presenters as well. Tremendous information. The people that are interested in the consortium that Matt Moynihan has been working on, we would love to get you in that, especially in the defense industry, just like Tokamak has said. They're not very they don't have a lot of fingers into the defense industry, and that's why we're here. We're here because this is mostly defense, and we want to hear from the defense industry, because like Michael made a comment, we don't know what we don't know. And until we sit down on these forums, have these open conversations, share these ideas, we're not going to know. So let's do it.
That's great. Very grateful of the suggestions that have been made for different applications that we may not have looked at already. So if you have any more, particularly ones that require very strong magnetic fields that are kept on all the time and need to consume very little power, then those are the killer apps for HTS. We'd love to hear from you.
Yeah, exactly.
I mean, you didn't address any medical. Are there medical applications for this?
So we didn't touch too much on that. We are looking at physical science and other things as well, like imaging.
Okay.
Mm-hmm.
Yes. Proton beam therapy is another one. So actually, this is the idea. You have a patient in the middle of a toroid that looks a little bit like Demo 4 actually, and is a very similar size, and you fire a beam of ions that are bent by the magnetic field, and they provide a much more targeted, basically attack on tumors, because they deposit their energy in a very much smaller distance than conventional ionizing radiation.
Okay. Now what about applications in non-destructive testing, maybe mining, and like ground penetrating radar type things? Would the magnetic fields penetrate, and could you image with them?
So mining is an interesting one. David and Michael, I don't know if you wanted to come in on the mining aspect. So
yeah, I'm just trying to get an idea of who within the community I need to share this with.
Yeah, we've looked at things like mineral separation using magnets in mining. And because of the very strong magnetic field, the possibility of separating minerals that can't otherwise be separated, weakly magnetic or paramagnetic materials, for example.
Yes.
Yeah, so
Okay.
could be relevant.
So David, if you wouldn't mind, on the YouTube channel, there was a presentation by a company called Smart Dry. And they use a liquefaction process to pull all of the metals, and actually they can pull out radioactive material, and one of the things that they can do is they can pull mercury out of water and out of ground, and that's something that is of interest in California with all the gold mining and all the mercury that they use for those processes to improve water quality. But if you could take a look at that presentation and see if there's applications there, and let me know, and then I can make those introductions.
So they were using magnetic fields to do that?
No, they're actually using liquids and some kind of coagulants.
Yes,
and vibration, but then they just get this large pile of metal.
Yeah.
And so there might be some applications there.
Yes, there might. Interesting. Yes.
Sounds interesting. Yeah.
Because at least you could separate out the ferrous and non-ferrous.
Yes. Yeah. Well, with these very high fields, even weakly magnetic paramagnetic materials are separable.
Yeah.
And if it's a high enough value application, for example, getting rid of radioactive contaminants, then it could be very interesting.
Yeah. So that would be nice if you could look at that and either get back to me directly or through Michael. That would be great.
So, have you looked into magnetic structures much? As in multiple components, multiple units that are not physically attached, but still are strongly bonded, such as through magnets.
No, I don't think we have.
Okay, so that's another one you can look into. I mean, if your units would work at a small enough scale, I mean, talking like a full unit for a decent field could be gotten down to a millimeter or less on a side. You could even take a go at the old utility fog concept, which is science fiction, but if someone can find a way to make it real, there's some potential uses there. I should know I have a patent on it for one of them.
I like it.
You have my contact info. Feel free to ask me more about that offline.
Yeah. Thank you. Cryogenics often provides a limitation. It's getting all the more practical, but there's certainly a size factor below which you can't. Yeah, you need a certain size in order to generate some cooling. But cryocoolers are pretty small now. You can get cryocoolers that are about this big that will deliver 40 Kelvin and a few watts. So it's changing.
Yeah, you need smaller to make a real strong go of this, but there's ways to make it smaller once there's a use for it.
Yeah, very good. Thank you.
So I'm gonna go back to Matt, and and people can leave. This is the whole ideation process here that we're kind of going through. So Matt, in your first slide, you showed the toroid and with the plasma running through there. Now, would you be able to, or is molten salt naturally ionized? And then, because there's such a thing as a molten salt reactor, and part of the challenge with those is just the heat. So if there was a way to keep it from actually making contact with the sides inside of a vacuum, would.
Okay, so a lot of fusion startups are using molten salts as their blanket material.
Okay.
General Fusion has done that, but there's also been talk about it in the ICF or IFE world. Excimer's looked at that, It was a concept as part of the LIFE program for a number of years at Livermore. And there's a gentleman, ex-Livermore, who specializes in that, is now consulting for Exemer about that specifically. The problem with that is that these moltens are often magnetically conductive. So if you put a tokamak, for example, with a molten salt around the outside, one of the issues you run into is that the field extends into the molten salt. And so the field screws up your beautiful pumping of this molten material around the outside. And there's the center that studies that in the academic world is Mohammed Abdu at University of California, San Diego, UCSD. He, for about 20 years, has had a research program going, looking at magnetic fields and molten salt and how they interact and how they behave and how they can fight each other. That's one resource. There's two other good resources. One is the Libra project at MIT, which is studying molten blankets, and the work done at Zap Energy, because Zap Energy wants to put their pinch in the middle of a spinning molten blanket. Actually, That's one of the flaws in the Zap Energy approach, is that you have this beautiful plasma in this pristine vacuum, and then you have this liquid metal around the outside, and the liquid metal sublimates, and particles come off the liquid metal and get into your nice plasma and screw up your pinch, which is a problem. That's one of that Zap knows that. Anyway.
All right, so I'm going to put you in touch with someone in the community that's working on using molten salt as a propulsion, as a propellant.
Okay.
So they have a molten salt. They have a design for a molten salt system and using it for propelling. So.
Okay. All right. Well, I really appreciate the time today. It was really fun to do this. I really hope that Tokamak Energy especially gets business from this. Nothing works for free. No one gets money for free. No one gets work done for free. And so that's the goal here, right?
Right.
Anyway. All right.
Yeah. Thank you, Eugene, and thank you, Matt, as well for the introduction. Yeah, so hopefully this is just the start. We'd love to work on some, white papers or concept papers with folks on this call. As I've said, both government as well as university and labs. We've got a long history of working with labs and universities, and as we mentioned, we're small in the U.S., so we're really happy to be partnering with institutions in the U.S. So hopefully this is just the start of conversations.
All right, thank you. Yeah, and reach out to me, reach out to Tokamak directly, and if you guys hear something and I'm not copied on it, please keep me in the loop, because part of what we do is help drive these things forward. One of the challenges that we identified is that people get sidetracked, especially within the federal government, and as a supplier or a contractor to the federal government, there's a fine line between being diligent and being annoying, and and we want to be the middleman there. So if anybody gets upset, they get upset with me and not you.
Fantastic. We won't get
Very
upset.
Good.
All right.
Very good.
Very
Thank
good.
you all.
All right.
Have a good
Thanks
rest.
Talk to you guys later.